Hello again. So I will try to more successfully talk about twin widths, and I want to convince you that it's a natural notion that could come up in many different contexts. There are many entry points to come up with this definition. And we'll see results from several works with Colin Génier, Hugo Giocanti, Eun-Jung Kim, Yannick Nechetril, Patrice Osona de Mendes, Amadeus Reynald, Sébastien Siebert, Pierre Simon, Stéphane Thomasé, Simon Toronchik, and Remy Vatrigan. So the first entry point is the class of cographs. So cographs are very nice. First, how are they defined? So single vertex is a cograph, and the union of two cographs is itself a cograph, and the complete sum of two cographs, where you put all the edges between your two cographs, is a cograph. So that's a recursive definition of cographs. And you see that there is a natural tree associated to those operations, where at the leaves you have single vertices, and for internal vertices you have two different labels that are either the complete sum or the disjoint union. And because of this tree structure, there are many problems that you can solve in polynomial time on cographs. So let's try with maximum independent set. So a single vertex, the maximum independent set is 1. If you have the union, you make the sum of the sizes or the union of the solutions. And if you have a complete sum, you can only take your independent set in one part, so you take the maximum of the two. So if you replace your tree syntactically by those 1 plus and max and compute the value, you get the maximum independent set. Another definition of cographs is that you can iteratively find two twins. So you could ask whether there is an alternative algorithm that would use now this definition. It turns out that there is one, and that corresponds to making this algorithm, which is recursive, but non-tail recursive, into a tail recursive algorithm or an iterative procedure. So we start with storing 1 at every vertex of our graph. So here there would be edges that I didn't draw. And the meaning of this is that there is inside the vertex an independent set of size 1, namely taking the vertex. So we'll update those weights so that it always captures the fact that there is a maximum independent set of the weights that you see on the vertex inside that vertex. So what do I mean by inside that vertex? So we'll merge vertices. So a vertice will correspond to subsets of vertices of the initial graph. And we will basically do the same thing. So now if we have two false twins, so they are non-adjacent. So if you want to include those 5 vertices in the solution, it dominates the common neighborhood of 5 and 2, so you might as well take 2. So you, if you take here, you take also there. So you would take 7 vertices in total. So you can merge them and take the sum. If you merge false true twins now, 5 and 3, you can only take maximum independent set in one part, so you take in the maximum, so here you make the max. So it's the same thing as before, and in the end you have a single vertex that contains the size of the maximum independent set. Fair enough. Can we go a bit further than cographs? So it seems that it's working quite well. Maybe we can solve maximum independent sets in a slightly more general class of graphs. So what about if you don't find exact twins, like 5 and 2 were, but at some point you're stuck with things that are almost twins, like 3 and 5, they differ only on the vertex labeled with 4. So in that case, you see that if I merge them into one vertex, and as in the case with cograph, I would record the maximum. What I'm forgetting is that there is a solution taking 3, those 3 vertices here, and 4 vertices there. So there is a way to take 7 vertices spanning the whole contracted thing. So I would need to also have this set of those two vertices, saying that I can fill those two vertices with my solution and get a value of 7. And it seems that if the errors are clustered into some bounded size components, we will still manage to solve maximum independent set in polynomial time. As it happens, this would be a definition of bounded rank weights. And anticipating in the definition that I will now give of twin weights, if you make the error more precise so that you can talk about the error graph, twin weights will be linked to the bounded degree of the error graph. So now maybe the definition of twin weights will make more sense, but we have to move from graphs to trigraphs, where in addition to the normal edges and non-edges, we have special edges. So they will be always in red. There are error edges saying there is at least one edge and at least one non-edge between those two subsets. So I have this vision that vertices are subsets of vertices of the original graph. And an operation that I can do is contracting two vertices. So they don't need to be adjacent. They can, but they don't need to. And so when I contract U and V, I merge them into a single vertex. What is in the private neighbors of U and V will now be linked with a red edge, because indeed there is at least one edge and at least one non-edge. And in the intersection of the neighborhoods, vertices x1 to x7, black edges will remain only when there was a black edge towards both vertices. So x3 or x6, for instance, they are linked in black to U and V, and they would remain linked in black to U and V. The rest of the trigraph, all the edges would remain the same. So that's a contraction, and you can iterate this contraction. So as we were doing in this second scheme with cographs, merging progressively our graph to a single vertex, we will do the same. So we'll merge our graph to a single vertex, and that defines many trigraphs along the way, and that is a contraction sequence. Now a twin width is just the least integer d, such that the graph has a contraction sequence where all the trigraphs that you encounter have maximum red degree at most d. So let's see on the same sequence what's going on. So we contracted E and F, we created red edges to A and D. So the overall maximum red degree, what matters for the twin widths, is now 2. Here 2 was never exceeded, so this would tell you that the graph has twin widths at most 2. And there are many simple properties that preserve bounded twin widths. So it seems that at first sight to be a robust notion. So you can, if you do complementation, or if you take induced subgraphs, if you add a vertex that you link arbitrarily to your graph, and we'll see if you do some modular decompositions, those things would behaves well with twin widths. So we will see the two that are in bold. So complementation, I said the twin width remains the same, so why you can take the same sequence. So you take the sequence for G and you apply it to G bar. And the trick is that the complement of the trigraph is to keep the red edges and to flip edges into non-edges, and vice versa. So this way you can see that when you perform the contraction on G bar, you get the complementation of the trigraphs. In particular, the red degree is the same. That shows this equality. And I said that it also modular decomposition is behaving well with respect to twin widths. So what do I mean by that? If you take any host graph, let's say here C5, and you replace at a vertex some other graph, here I chose P4, and this is a module, so everything that is outside is seeing entirely the P4 or not at all. And you can replace the other vertices of the C5 with other graphs. It doesn't have to be P4, but here that would be the lexicographic product of C5 and P4. What will happen in general is that you can contract within a module, within a subset here, and get the maximum red degree, the twin widths of this particular graph here, the P4, so in that case 1. And you will never create red edges that are leaving this subset. So you will have at least the twin widths of your modules. And once you're done with contracting the modules, you have the host graph that you can contract. So all those graphs that appear in the modules and the host graph, you take the maximum twin widths of all those things, and this is the twin widths of the entire graph. Now let's move on to graph classes that could potentially have bounded twin widths. So let's start with a simple graph class, trees. So trees have twin widths 2. So this is a way to show that. So we'll have two rules. Either we have two leaves that are twins that share the same parent and we contract them. So here I did it here, and now I don't anymore. And in that case I will contract a deepest leaf with its parent. So we'll contract this leaf with its parent here. And I get this star graph. Again, I don't have two leaves that are twins, so I go with my second rule and I contract deepest leaf with its parent and I get this. So now I have two leaves that are sharing the same parent, so I will contract them. And you see that if I apply the first rule of contracting twin leaves in priority, then I will never create a vertex with red degree 3. So all the trees have twin widths at most 2. There is a far-reaching generalization of this fact that graphs with bounded rank widths have bounded twin widths. So rank widths, bounded rank width is more general than bounded tree widths. So let me give you an intuition of what that is. So graph has bounded rank width if there is a tree layout, so a tree where the leaves are labeled by vertices of your graph, such that all the edges of the tree, so when you remove them, they define a cut between one part of the tree, the other part of the tree, so they define bipartition of your graph. In this bipartition, the number of neighborhoods from one part to the other is bounded. So that is actually a definition of bounded Boolean widths, but those are functionally equivalent, so you can take it as the definition of bounded rank widths. And the reason why bounded rank widths has bounded twin widths is that you can find a small tree that is big enough that you can find two vertices inside it having the same neighborhood outside of the tree. So in the definition of at least the definition that I gave you of rank widths, the number of neighborhoods was bounded. So if this is large enough, but not too large, it will contain two vertices with the exact same neighborhood outside the subtree. So you can contract them, and if you operate like this, you will only create red edges that are clustered into some small trees that are not leaving this tree. So the red degree will be bounded, in particular because if I look at the graph induced by the red edges only, its connected components are of bounded size. It happens that this is an if and only if, so you can define rank widths that way with a contraction sequence. And because tree width is a sparse version of rank width, you could also define tree widths with contraction sequences. And you can also define linear rank widths and path widths. So linear rank widths, it's the same where you replace the tree by a path. Now you would need to characterize linear rank widths with contraction sequences to tweak a bit the way we were putting the red edges, but then it will correspond to the total number of red edges. So if the total number of red edges at any point is bounded, then this coincides with bounded linear rank widths, and path widths would be the sparse version of this. Now let's try still some fairly simple class, but which has unbounded rank widths, the class of grids. So grids have twin widths at most 4, and there is a simple contraction sequence that I will show you now. So you can contract this top edge here. So I can not only show that the twin width of the black grid is 4, but actually the red grid, which is a bit more difficult, is also 4. So I will take actually this trigraph. You'll see why. So if I contract this edge, I get this. Now I'll contract this edge, I get that, and so on and so forth. And you see that I'm back to the same grid, -1 column. So I can iterate this, get the red path, and contract the red path. So this shows that grids have twin widths at most 4. And this would extend to higher dimensional grids with a dependency on the dimension for the sequence. Now I want to emphasize on the fact that twin widths is really not about identifying near twins iteratively. And maybe the beginning of the talk confused you with that. So just to be sure, so consider this complicated graph. So it's the power set graph, and it contains, if I make 4 large enough, it contains all the bipartite graphs as induced subgraphs. So this object is complicated. I don't want it to have bounded twin widths, and it doesn't. But it has a sequence where I'm only contracting near twins. So namely vertices differing only on being adjacent or non-adjacent to 1, and agreeing on the rest. So 1, 2, and so on. So I could collapse this graph to this and proceed now with 2, 3, 4, and there is a complete sequence that would all the time merge near twins that are differing on at most 1 neighbor. But because we track the errors in the edges, we made a lot of errors involving 1, so it doesn't have bounded twins. And this is what is crucially making the definition of twins have good algorithmic properties. Okay, so there are examples with unbounded twin widths, it seems. So we cannot assume that everything will work. What about planar graphs? So because for grids it was so easy, we could think that we'll find something local strategy for planar graphs, but you cannot. So for instance, this graph here, it's an example where there is no contraction that preserves planarity and preserve the bond of 4 here for the red degree. And I could make 4 arbitrarily large. So you will not manage to find something of the form, give me a planar trigraph, I know that I can contract 2 vertices and not increase the twin widths. This is not true. And so we need more things, and it will make us define twin-widths in a more general setting. So for matrices and for binary structures in general. So I will stick with 0, 1 matrices, but you see that this definition makes sense if I would be on the finite alphabet here. So let's try to recast what we were doing with our contraction sequence on graphs on matrices. So we're taking 2 vertices, so now we'll be taking 2 columns or 2 rows and merging them into 1. So here you see the adjacency list of vertex, same here. So whenever they agree on the adjacency, you put the same value. And when they disagree, like for instance 1 and 0, we're putting an error edge. So here we'll put an error symbol. So we're basically doing that. Now the twin-width, you would read it as the maximum number of error symbols in one column or in one row. And maybe something is bothering you that I can only contract, so I'm in a bipartite setting where I can only contract 2 columns or 2 rows, but I cannot contract, for instance, a row with a column. Right, so there are many reasons not to worry about that. But if you want a notion to get the same notion of twin widths of your graph, you could start with your adjacency matrix, which is symmetric, square and symmetric, and whenever you perform a contraction of, let's say, 2 columns, you perform the symmetric contraction of the 2 rows. But again, we will not worry about this, so maybe it's better to think in the bipartite setting. Another equivalent viewpoint is to imagine that you have a finest partition on top of your matrix, so it's partitioning the column set and the row set into here singletons, and we're merging 2 parts and recording when there is a zone which is no longer constant, putting it in red. So here there would be 2 of them. And now the red degree, or the number of error symbols, you read it as the number of red zones within a single part. So we'll call this error value. And the twin widths would again be more or less equivalent to refinement sequence of merging, or I should say not refinement sequence, a coarsening sequence of merging parts, that the maximum red degree remains within your bound, and that you end up with the coarsest partition where you have 1 part for all the columns and 1 part for all the rows. So that would again give you something equivalent to twin widths. And we will now focus more on divisions, which is a particular case of partitions where you partition into consecutive sets of rows and columns. So for instance, all what I represented there were divisions. Okay. So there is a couple more things that I want to define. The notion of a grid minor and of mixed minor. So what is a grid minor? A grid minor is, so a T-grid minor is a T by T division. So here it's an example with T equals 4. So it's a 4 division of your matrix, such that in every cell there is at least 1 entry 1. So if I want to generalize the definition to finite alphabets, actually I should put that the cell is not full 0. So this is a 4-grid minor, and we will say that the matrix is T grid free if it doesn't have this structure, if it doesn't have a T grid minor. So this particular matrix is not T grid free, 4 grid free. Sorry. And the mixed minor will be the same, but we replace not being full zero by not being horizontal nor vertical. So it's again 3 mixed minor is a 3 by 3 is a 3 division where every cell is not a copy of the same column vector or nor the copy of the same row vector. And there is a local witness of that. So you can witness that something is not horizontal nor vertical by a contiguous 2 by 2 submatrix. So here I represented this thing that we call corner. Again, a matrix is a T mix free if it doesn't have a T mix minor. So this matrix is not 3 mixed free. And now I can come up to finally a statement. So there is a characterization of twin widths with mixed minors. So here I just represent in one direction, which is the difficult direction, and that would be the helpful direction to bond the twin widths on classes of graphs. So let's parse this statement together. So if your graph has a T mix free adjacency matrix, then the twin widths of the graph is bounded by a function of T. So I put A in bold because it hides something complicated to have a particular adjacency matrix. Because in this definition of T mix free, the order of the rows and columns matters. So the ordering of the vertex set here will be important. So it's this is hiding the existence of a vertex ordering such that the corresponding adjacency matrix has some property. Let me just sketch how we prove this thing. So the first step is to find a division sequence, which is more than what we want. We just want a contraction sequence in the definition of twin widths. But it doesn't have bounded error value. That would be twin widths, would be done. It has just bounded mixed value. So what is mixed value? I won't give you precise definition, but it's more or less the same when you replace the non-constant zones for the error values to mixed zones for the mixed value. So there are some technicalities here, but we won't enter into this detail. So what happens is that here we just do some greedy procedure where whenever we can merge two parts without increasing this mixed value too much, so it doesn't exceed this bound, then we do it. And we claim that we cannot be stuck. So if we're stuck, we can show that there is a large density of mixed zones. And we assume that in that ordering, there was no T mix minor. So we just have to go from a large density of mixed zones or corners to finding them in a two-dimensional way, in some grid thingy. And this statement seems obvious. Actually, it was for some time a conjecture, and it's really not obvious to show. There is only one proof, and that is a beautiful proof. So this is Marcus-Stadler's theorem that says that for every integer k, there is another integer ck, such that every 0-1 matrix with density ck of 1 entries per row and column has this k by k division with at least 1 entry 1 in each zone. So now if we interpret mixed zones with 1 and non-mixed zones with 0, it's just applying Marcus-Stadler's theorem that tells us that, okay, this cannot happen by assumption, So we're done with step 1. And step 2 is to now say, okay, we didn't need a division sequence, a contraction sequence is enough, but we want the error value to be bounded. So what happens there is that you look at your division sequence, and within parts of the division sequence you cluster things that are now not consecutive necessarily, but behaving the same way outside of the mixed zones, and this leads you to the contraction sequence. Okay, so all this is following quite closely a very nice algorithm by Guillemot and Marx, solving a problem called permutation pattern, where you're given two permutations, a small permutation sigma and a host permutation tau, and you want to know if sigma appears as a subpattern in tau. So here it would be a yes instance, and it was open if this param is FPT, so fixed parameter tractable in the size of sigma. So we want something function of sigma times polynomial in tau, and Guillemot and Marx showed that not only it was, but there is an algorithm which is linear in tau for that. So I won't enter into the details of how closely we're following Guillemot and Marx. Maybe I should briefly tell you how it goes still. So what they do is that they start with the host permutation, and they make some merges. So they start with the 1 entries of the host permutation, and they merge them into larger and larger rectangles containing them. And they also apply Marquis-Larger's theorem. So either in the case where they find a large grid minor, they are done, because not only sigma will appear, but any permutation of the side of sigma will appear. And if not, then their sequence of merges gives some structure that is exploitable algorithmically. Now you might be guessing what's going on. So this good structure on the permutation, they call it width, is if you generalize this width to graphs, you actually end up with units, and they even anticipate that. So this is a quote from the paper. So that's a most obvious entry point through the definition of twin widths. Okay, so now what to do with this characterization? So here we have just one direction. Well, we can now more easily bound the twin widths of a class of graphs. So we don't need to find the contraction sequence. We just need to order the vertex set of its members. So we take a graph from a class, and we say, okay, this is a good way to order its vertex set. And if indeed the adjacency matrix that we get along this order is T-mix3, we know, and it's effective, that the twin width is bounded. So we'll see a couple of examples. So the first example is unit integral graphs, so intersection graphs of unit segments on the real line. So here the order makes no doubt. We want to order by left endpoints. So if you do that, you would get an adjacency matrix looking like this, and you could convince yourself that there is no 3 mixed minor. Whenever I take a 3 division, there will be a zone that is not mixed. So in that case, there is this zone which is constant. And the second example will be a generalization of planar graphs. So KT minor free graphs. So here I'm just insisting that it's the graph minors that you know. It's not those grid or mixed minors. So graph minors that you obtain with vertex deletion, and edge contraction. And planar graphs are exactly graphs excluding K5 and K33 as a minor. So we'll use the previous theorem to show that KT minor free graphs have bounded twin widths. So we'll only show it in the case where the graph is Hamiltonian. So if the graph is Hamiltonian and we're given the path, we can order along this path. And now assume that there is a large mixed minor. So in particular, it's a large grid minor. In particular, in every zone, you have at least one entry 1. So you can first place yourself off diagonal and still have a large grid minor. And now you know that A1 to AT, B1 to BT do not intersect. Now, because we are along a Hamiltonian path, we can edge contract along A1, along A2, and so on. So we can do this for A1 to AT, for B1 to BT, and create what is a KTT minor, because there is at least one in every zone. In particular, we have a KT minor, and it contradicts the fact that we were from a KT minor free class. So now if we don't have, if the graph is not Hamiltonian, then we have to emulate the Hamiltonian path with some special XDFS. We won't do that. So there are many classes that not only have bounded twin widths, but where we can find efficiently a contraction sequence. We saw many of them here. You see down the list something that are quite surprising, like if you take any graphs and vertices and you subdivide sufficiently many times every edge, it has bounded twin widths, and also some families of expanders have bounded twin widths. You won't imagine those kind of graphs to have this kind of structure. So it begs the question whether we can do whether we can solve primes faster. And if you remember the very beginning of the talk, you might guess that yes, we can. So we cannot for a prime like max independent set, but we can in the parameterized setting. So if we try to solve k independent set, which normally doesn't have an FPT algorithm in k, doesn't have an algorithm of the form function of k times polynomial, now we will be able, in the case where we have bounded twin width graphs and we're given a sequence. So we're given this sequence. What we want to do is to look, so those are trigraphs, we want to look at the red graphs, so the graphs induced by the red edges, and store for each connected subgraph of size at most k a best partial solution inhabiting this those vertices. So that will become clear on the next slide. But let's check that this would in principle give an FPT algorithm. So we're dealing with graphs of degree at most d. By definition of d sequence, the red graphs have degree at most d. So indeed, in graphs of degree at most d, if you look at connected subgraphs of size at most k, they are d to the 2k times n of them at most, and I have n red graphs, so I get this n square, but actually we'll see that we don't need the square, so we have something linear. So we get something if I really treat d as a constant, which is a single exponential in k times n. Okay, so the two extreme points, you already know them. Initially, we will, so the red graphs is empty, so its connected components, its connected subgraphs, sorry, are singletons, and we will sort that there is a solution of size 1 in every vertex. And eventually, everything is merged into a single vertex, so here, if there is a solution of size k initially, we will want to find it in this unique vertex. So what we need to do is to go from the partial solutions of gi plus 1 to the partial solutions of gi. And if we can do this, we will be done. So let's say we go from this gi plus 1 to gi by contracting here u and v. And now in gi, we're asking what's the best solution intersecting, well, those vertices that you see with the gray dot. So what we know is the partial solutions in the previous graph in gi plus 1. So you see that to intersect Z, you have three possibilities, either intersecting V but not U, or U but not V, or both. There will be sometimes solutions that are not possible. So for instance, here, inhabiting U is not possible because there is a black edge towards something where we also want to inhabit. So, but in general, you would have to consider three possibilities, as we said, either only U, only V, or both. And for that, look at the best among those three solutions. So the solutions mapping to the gray dots here, it corresponds in gi plus 1 to at most d plus 2 connected components. So here we have them with different colors. So here you know for the blue component here you know the best solution. For the orange component you know, and so on. So you can sum the best solutions here and come up with something, and you will take what is best among the three possibilities. And basically that's it. Why we don't need quadratic time but linear time is enough is that we don't need to update solutions that are too far away from the contraction. Okay, and this scheme works for other problems. You get for these problems here a single exponential, and for subgraph isomorphism or induced subgraph isomorphism, something close to single exponential parameterized algorithm. So is there something more general here? And there is. So we can precisely define where we can solve problems faster, and it's for problems in the framework of first order model checking. So I will define first order model checking on an example. So here the question is whether a sentence phi is satisfied on a structure on a graph. So if you look at this sentence here, it says are there k vertices such that whenever I pick a vertex, it's either one of those k vertices or adjacent to one of those. So this is k dominating set, and you see that why it's first order. Well, I can quantify only over single vertices. That's another example where here we want k vertices that are distinct and non-adjacent. So this is k independent set, and there are many problems that you can express like this. And let me define a couple more things: Nefo interpretations and Nefo transactions. So Nefo interpretation is just a way to redefine the edges of your graph. So you say, okay, I'm not following the rule E, I'm following the rule phi for the edges. So here, if you negate E, you get the complement of your graph. If you look at the second formula here, this corresponds to squaring your graph. So that's an interpretation. So from one graph, you create one graph. And there is something more robust that from one graph creates a collection of graphs, which is a Nefo transduction, where you initially can color your graph with a constant number of linear relations. So you put the constant number of colors. This comes non-deterministically. Then you interpret. So the interpretation now can talk about the linear relations, being colored red or blue or green. Again, it defines some edges, and then you're allowed to take an induced subgraph of this, and you don't care about the colors anymore. So you remove things, and you get one graph. So you don't get only one graph, because there are many ways of coloring with a constant number of colors, so you get a collection of graphs. So with a Nefo transduction, you go from one graph to many graphs, and you can extend this notion to classes. So you can apply a Nefo interpretation or a Nefo transduction to a class of graph, and it's exactly what you think. It's the class which is the union of the Nefo interpretation or the union of the Nefo transduction. And a class is said dependent if you cannot get all the graphs as induced subgraphs of a fixed interpretation of your initial class, and it's monadically dependent if you cannot get all the graph with a fixed transduction of your class. So FO model checking is in general graphs AW star complete, meaning that it's very unlikely that there is an FPT algorithm. And if you look at the definition of dependent, you might think that on classes that are not dependent, so they are called independent, we cannot get an FPT FO model checking. It's almost true because you can emulate all the graphs with your interpretation, but you would need the interpretation to be effective and not to blow up too much the graphs when you go from one class to the other. But morally, it seems hopeless to solve FO model checking in FPT time on independent classes. And there is an optimistic but believable conjecture that on all the other classes, on classes that are dependent, you can find an FPT algorithm. So it's a conjecture that is probably a bit folklore, but it's made very explicit in a paper by Kojarski et al. And now I will say that the class is tractable as a shorthand for FO model checking is FPT on that class. So this is a very nice conjecture, and there are many classes that are known to be tractable. They are obviously dependent. So this is what we know currently on classes where FO model checking is FPT. So I won't define all those things, but for classes that are closed under taking subgraphs, we know the final answer in the so-called nowhere dense classes. There is an algorithm for those classes, and this is as far as we can get. For classes that are not nowhere dense but subgraph closed, we know that FO model checking is not tractable. And in the in classes that are only closed under taking induced subgraphs, not subgraphs, so now you can have dense classes, you can have cliques, because before, if you are closed under subgraphs, if you have cliques, you have all the graphs. So now you have things that are dense, and this is what we know. So the classes where FO model checking is FPT, with the caveat that for bounded twin widths, we need the D sequence to be given. So in general, we cannot find an approximation that would give big O of one sequence, but we should relativize this caveat, because on all the classes that, if you remember this list of classes of bounded twin widths, we knew how to efficiently compute a sequence. And as some kind of byproduct of the algorithm, we get this very robust property that if you take a class with bounded twin widths and you apply any transduction, what you get still have bounded twin widths. So I want to give you a setting where this caveat disappears and where twin widths is even more useful, so to speak. But before that, let me just tell you about small classes. So we'll say that a class is small if the number of graphs, when they are labeled bijectively, so you label their n vertices with the integrals from 1 to n, you have only exponentially many of them. So there is this n factorial to account for the labeling, but then there is just single exponentially many of them. So we showed that classes of bounded twin widths are small, and it generalizes and unifies the Stanley-Wolf conjecture that can be rephrased as permutation classes of permutations avoiding a pattern are small, and the fact that KT minor free graphs, KT minor free classes are small. That was proved by Noreen, Seymour, Thomas, and Wallen. So yeah, it unifies those things, but it crucially depends on the proof of Marquis-Tarder's theorem. So we need Markov-Stadler theorem to prove this, and it's also using an opening step in the paper by Noreen et al. And it turns out that it's for graphs of bounded degree, the only argument that we have to give to say that those classes have unbounded twin-weights. So if you look at subcubic graphs, it's not a small class, so we know that collectively they have unbounded twin-weights, but yet we cannot provide an explicit construction and say, okay, this particular graph, it has bounded degree and large twin-weights. So it could be tempted to conjecture the converse for hereditary classes. It turns out, and we did it for some time, but it turns out that we also, recently we refuted the conjecture. So the converse does not hold. So this setting where the caveat of finding the sequence disappears is the setting of ordered graphs, or more generally ordered binary structures. And here it's very nice because we know how to efficiently compute a sequence, or how to efficiently approximate a good sequence. And all those notions that could not coincide for unordered graphs, so bounded twin-weights and being tractable, because bounded twin-weights and bounded degree are incomparable, and bounded degree is a tractable class. It's a class where f-of-L checking is FPT. But here, when we move to ordered graphs, all those things are equivalent, and they are equivalent to bounded twin-weights. So it's equivalent that the class has bounded twin-weights, that it's tractable, dependent, monadically dependent, small, and that the growth is less than n/2 factorial, so it has subfactorial growth. So it's all in one. It's saying a lot of things. So that twin-weights is capturing the tractability of those classes. That dependent and monadically dependent coincide, which is not known for unordered graphs. And also, when you look at the equivalence between 5 and 6, it gives a gap in the growth of ordered binary structure, ordered graphs. That is solving a conjecture by Balogh, Bolobash, and Morris. And it seems that twin-weights is the right delineating line between what is easy and hard on ordered graphs. So twin-weights gives you the structural characterization of dependent classes in that context that is currently missing to tackle Gajarski conjecture. So for that conjecture on general graphs, we would need probably some structural insight on what it is that makes a class dependent. And well, we know that we'll have to generalize nowhere dense classes and bounded twin-weights classes, and it's a very exciting ongoing line of works. A couple more things where twin-weights can pop up. So if you look at what you can get by means of a transduction starting from a given class, well, you can, so we characterize bounded twin-weights as FO transduction of a permutation class. So by default, it's assumed to be closed by subpermutations. That is proper, that is missing one pattern, one permutation. So bounded twin-weights is equivalent to being a Nefo transduction of a proper permutation class. So there are many statements of that form. Maybe the most well-known are with rank widths and tree order. So you have bounded rank widths if and only if your transduction of an FO transduction of a tree order or an MSO transduction of a tree. And you have the same with linear rank widths if you're the FO transduction of a linear order or the MSO transduction of a path. So you see it's again a way to see how twin-weights generalizes rank widths. So you go from tree orders to proper permutation classes. And if you put the results of the previous slide and some observations in the first paper of the series, you get that bounded twin-widths correspond to reducts of monadically dependent classes of ordered binary structures. So let's try to unpack that. So show both directions. So if you're a monadically dependent class of ordered binary structures, we saw that this was equivalent to bounded twin-widths. And in particular, you will have bounded twin-widths. So the reduct is just that you ignore the order. Now in the other direction, if you're of bounded twin-widths, then there is a canonical order such that all your contractions will be on things that are consecutive. So when you add this order to your structure, you don't change the twin-widths. So you keep the twin-widths bounded. But now you're in this older world where bounded twin-widths is equivalent to monadically dependent. So this gives you the other direction. Right, and I want to conclude something a bit unrelated, but that gives you another use of twin-widths that is quite neat and simple, you'll see. So a class is said chi-bounded if you can bound the chromatic number in terms of by a function of the clique number. So we showed that twin-width classes are chi-bounded with this binding function of twin-widths plus 2 to the clique number minus 1. So you can color with that many colors. It's an open question whether, so you see the dependency in the clique number is exponential. It's an open question whether it can be made polynomial. So for bounded rank widths, the special case of bounded rank widths, we know now that it's a result of Bonnet and Mikhail-Pilichuk that those classes are polynomially chi-bounded. For bounded twins, it's open. So I will finish with this very simple proof that triangle-free graphs of bounded twin-widths can be colored with D plus 2 colors, which is contains the essence of this. The rest is just some induction, but the essence is here. And what we will do is to start from the end of the contraction sequence. So we'll start where we have just one vertex and give it color 1, and we will rewind the sequence and we'll try to update the coloring so that it's proper and it's never using more than D plus 2 colors. Two cases. So now when you rewind, you're not merging vertices, you're splitting them. So we go from GI to GI plus 1. So two cases. Either the vertex that is being split is only incident to red edges. In that case, by definition, you know that its degree is at most D. So here you see D plus 1 vertices, here you see at most D plus 2. So there will be one of the D plus 2 colors that you can use. Good. Or the vertex that is being split is linked to at least one black edge. But what is a black edge? Remember, it's a biclique between the two subsets. So when they split, it cannot create a red edge or a black edge, because that would mean an edge, and that would form this edge inside the subset, would form a triangle with this biclique. So when it splits, it's an independent set and you can keep the same color, and that's it. It's a very simple scheme. I will conclude here and recap the main open question. So we still need to find a way to approximate twin widths in general graphs when you don't have a particular class of graphs that you're targeting. The conjecture of Gajarski et al. Is very exciting. Getting explicit constructions of graphs with bounded degree and unbounded twin widths. We talked only about algorithmic applications getting exact solutions, but getting better approximation is also something very interesting, and where we have some preliminary results, but there are still a lot to do. As we saw previously, the making polynomial the chi-boundedness of classes of bounded twin widths, and do linear algebra faster on matrices of bounded twin widths. So I thank you for your attention. Under normal circumstances, I will be taking questions now, and it's a bit of a shame that it couldn't work like this. I apologize and thank you for your patience, and yeah, really don't hesitate to send me your questions by emails. I will be very happy to answer them. So thank you again, and goodbye.